Unit 5, Day 2, Optimum Surface Area and Volume of a Cylinder. So recall from the last lesson that we learned that the optimum or best rectangle is actually in the form of a square because it maximizes area with a given perimeter and it minimizes perimeter with a given area. Let us now use that idea from before that the optimum rectangle is actually a square and apply it to a cylinder, where we are looking to maximize the volume and minimize its surface area. So if we look at this cylinder from the side, what shape do we see? So you should see a rectangle right here. I'm highlighting it for you guys if it's not clear enough. Moving forward, remembering the last lesson, in order to have an optimum rectangle or square, what needs to be true about its dimensions? So remember that the formula is area equals s squared, meaning all the sides are equal, which you should know that all sides of a square are equal. So if we look at the square here, the thing that has to be true about these dimensions are the height has to equal this side for it to be a square, which this side is actually the diameter of that circle. Therefore, the answer to this question is that the height has to equal the diameter. So knowing that, let's determine the formula for the minimum surface area of a cylinder and the maximum volume of a cylinder. Now that we have figured out the one condition that needs to be true to create an optimal cylinder, let's derive the formula for the minimum surface area. So we know that the formula for the surface area of a cylinder is as follows. Surface area is equal to 2 areas of a circle plus the area of one rectangle. And we know that the area of a circle is pi r squared and the area of a rectangle is length times width. Now we'll expand this a little bit more, so we'll keep the area of the circles, but we know that the length of the rectangle, so this over here, this line that I'm tracing, is actually equal to 2 pi r. And if you don't know where that came from, just go back to the unit that we learned the equations for the surface areas of a cylinder. And finally, this width is actually equal to the height, which we know is actually equal to the diameter. The final thing we need to put in is we know that diameter is equal to 2r. And now we can combine these together. So surface area is equal to 2 pi r squared plus, if we multiply these terms together, we get 4 pi r squared. And finally, since these are like terms, we can add them together. So the surface area formula is equal to 6 pi r squared. And that will give us the optimal surface area or minimum surface area. To find the minimum volume formula for a cylinder, we will use the same formula we learned before, but we will plug in our restriction that height has to equal the diameter. So if you remember back, the volume formula for a cylinder is equal to the area of the base shape times the height of the cylinder. So the base shape is a circle, therefore the area of the base shape is pi r squared. And the height of this cylinder is equal to the diameter. Now we know that diameter is also equal to 2 times the radius, so it's in our best interest to change it to that because this part of the formula is already in terms of r's, so we can actually combine these together and only have one variable. Finally, let's combine these together and we get 2 pi r cubed. So we have finally derived the optimal equations for the surface area and volume of a cylinder. Let's now look at some examples. So determine the maximum volume that can be held by the cylinders with the surface area of 100 centimeters squared. So let's use our surface area formula that we derived above, plug in this number, find the value for the radius, and then we can use that value in the volume formula to come up with the actual volume. So from above, we know surface area is equal to 6 pi r squared, and we know to use these formulas because the question says determine the maximum volume, so we know what's our optimization or maximum and minimum equations. And now let's plug in our 100 for the surface area, and let's solve for r. So let's divide both sides by 6 pi. These cancel out, and we're left with 5.31 is equal to r squared. And finally, let's take the square root of both sides, and again these will cancel out, and we're left with 2.3 centimeters is our value of our radius. So let's take this value and plug it in to the volume formula to find our maximum volume. So volume is equal to 2 pi r3. And now let's plug in that 2.3 centimeters for our value of r. And if we plug that all into our calculator, we're going to get volume is equal to 76.45 centimeters cubed. So therefore, the maximum volume that can be held by a cylinder with the surface area of 100 centimeters squared is 76.45 centimeters cubed. Moving on to another example, determine the minimum surface area required to contain 500 centimeters cubed in a cylinder. So let's use our volume formula from above, plug in this value for volume and solve for r. Then we can plug in that value for r into our surface area formula and actually calculate the surface area. So we know from above that volume is equal to 2 pi r cubed. We'll plug in 500 for volume and solve for r. So let's divide both sides by 2 pi, and these will cancel out, and we're left with 79.58 equals the radius cubed. Finally, let's take the cubed root of both sides, and these will cancel out, and we're left with 4.30 centimeters for our radius. Now let's take that value and plug it into the surface area formula. So from above, we know that the optimal surface area formula is equal to 6 pi r squared. And now let's simply plug in our value that we just solved for r, 4.30. And if we plug that into our calculator, we get the surface area is equal to 348.53 centimeters squared. Just remember that surface area is always squared and volume is always cubed.